Now, lucky for me, I'm not a modeler, I'm an observationalist. So our job as observationalists is try to collect observations and use the patterns that we find to understand the processes that are modifying the clouds so that we can give the modelers targets or goals for them to achieve in their simulations. And there's no way any individual can do all of these different pieces at the same time. So we just pick little bitty bits and pieces and try and understand it, and then as a whole it comes together and you get the full picture. So one of the things that we've been working on and studying is the process of drizzle in these marine stratocumulus clouds. Drizzle is important because it's been implicated in previous studies in the breakup of the cloud. So I'm going to try and step through this little loop here, which shows the stratocumulus deck off the coast of South America. So this is the South American coastline here. And as I step forward in time, you'll see these little pockets opening up in the cloud deck. And these are called pockets of open cells. And since we have to have an acronym for everything, we call them POCs. Now, POCs are important because they break up the cloud and they allow sunlight through. So from a radiative perspective, understanding the processes that start and stop POCs is very, very important. And one of the key processes in this is drizzle. So drizzle is important because it not only removes liquid water from the cloud, so the cloud, it's sort of draining its reservoir of available moisture. But there's also some dynamical impacts of drizzle that we've been studying that turn out to be quite important. So one of the basic things that we've been looking at is boundary layer mixing. So this is more of a boundary layer process, but it modifies the cloud. And what we see is a very, very strong diurnal cycle. So at night, given a black background up here, we'll pretend this is night, you have a lot of cloud top cooling, and that serves to mix the rest of the boundary layer. So by mixing, what I mean is moisture is flowing up from the sea surface, and you have downdrafts bringing moisture back down in the form of precipitation. So you have a well-mixed boundary layer. You can think of this like a pudding that looks all the same. So whether you're in the cloud or at the surface, you have plenty of moisture available, and that's not a problem. During the day, a slightly different scenario sets up where you have the shortwave heating from the sun, which offsets some of the cloud top radiative cooling, and it shuts off the mixer. So if you're mixing a cake, you turn off your blender, and you lose the ability to mix the moisture from the surface back up into the cloud. So what this does is it cuts off the moisture source to the cloud, and this cloud starts to thin and break up. And then again, from a radiative point, this is very, very important. We can look at this in terms of the boundary layer mixing, and I won't go into too much detail on this plot because it's a little bit busy and complicated, but if you just look at the top plot, it's a vertical profile of the water vapor mixing ratio as a function of time. So we're stepping through time on the x-axis, and then height is on the y-axis up here. And one of the things that you can see is this buildup in the afternoon, say from noon to 6 p.m., where water vapor mixing ratio begins to accumulate at the surface. And this is again due to that lack of mixing in the boundary layer. So when you turn off the mixing, the water starts to just pool at the surface, and that means it's not available in the cloud. So you're seeing the cloud thinning here. After sunset, the mixing kicks back in, and you get a much more evenly distributed profile of water vapor throughout the depth of the boundary layer. The cloud has access to the moisture from the underlying surface, and it's very happy, it's very persistent, and it can reflect radiation. So these results aren't necessarily unexpected. People have sort of done this before. The thing that's new and very exciting is the resolution which we're able to look at these features and sort of isolate these processes. And that resolution is due to the fact that we have a lot of data. In 2008, there was a National Science Foundation and NOAA funded experiment called VOCALS. And VOCALS went into the Southeast Pacific with a series of airplanes and a NOAA ship, the Ron Brown, which we put a radar on the ship, and they went out and they took lots and lots of measurements over the course of, say, a month and a half, and gave us all that data. So with all that data, we're able to look at these processes and resolve these processes with much greater detail and much greater precision and a better understanding about what's going on. And that's really catapulting our understanding of marine stratocumulus clouds forward in the future. The application is, of course, our models aren't getting a process right. So we go out, we collect the observation, we think we have a better idea of the process and how it works, and we're able to give that as information to the models, and they can try to better simulate what's actually going on in the real world, and that's extremely valuable. Um, our group's not the only group doing that. There's groups all across the United States and all across the world that are working on similar things, all with this goal of improving our ability to simulate these very complicated clouds. We're a precipitation group, so we do lots of studies about precipitation, specifically patterns and processes, and so we have our hands in lots of different buckets.